So take a look at number one. Number one uses something we call a bearing. A bearing is a way to measure what direction you're traveling in a boat or on an airplane, or if you have a compass and you have to walk a particular direction. Bearings are very simple. So an example of a bearing is like south 40 degrees west. What that means is face south, so face this direction, north, east, southwest, for those of you who don't understand how maps work, and turn toward the west 40 degrees. So this angle here would be 40 degrees, and this bearing is south 40 degrees west. Now, technically, we could also call that west 60 degree, or yeah, don't trust Abram. West 50 degrees south. But bearings are never listed that way, right? If you face west and you turn towards the south 50 degrees, then you would be going in the same direction. But bearings are always with reference to north or south. So you could do south 40 degrees west. If you were in quadrant 1 or 2, it would be north, for instance, 15 degrees east. Where would that be? It would be right here in quadrant 1, where that's 15 degrees. So you start either facing north or south, and then you turn so many degrees towards the east or west direction. That's pretty easy, right? Number 1. Lighthouse B is 8 miles east of Lighthouse A. So, let's draw a picture, because I like pictures. A. Where would Lighthouse B land? East. Right. Don't follow Braden into the woods with a compass. If your glasses are far-sighted glasses, reading glasses, you can. If they're not, welcome back, those of you who missed that long conversation. We would leave Colette a note, but she's here. Okay, back to math. So, this distance here is 8 miles. A boat leaves Lighthouse A and sails 6 miles. We have no idea which direction it sailed in. Okay, we just know that the boat left A and traveled in 6 miles, or sailed 6 miles. At this time, it is sighted by Lighthouse B. If the bearing of the boat from the lighthouse is south 71 west, how far is the lighthouse from the boat? So the lighthouse looks south, so looks this way, and then turns toward A 71 degrees. The boat left A, but the boat can be seen from Lighthouse B. So this angle there is 71, and that's not the angle we want, obviously. We want this angle, which is 19 degrees. Okay? And somewhere along this line is the boat. So I'm just going to put the boat here. Where does the 6 miles go? From A, we can call this C. That's a good idea. 6 miles. Okay? So we want to know, basically, what is the length of little a? How are we going to figure that out? Law of sines. Here we go. Sine of 19 over 6 is equal to sine of, we can't do A. We have to do C over 8. 8 sine of 19 divided by 6. What does that tell us? That tells us that the lighthouse didn't lie to us, right? The lighthouse is not making this up. Well, we can't guarantee they're not drunk. They still might be. But at least they're not seeing things. That's true. No hallucinations. It might be. So angle C is 25.7. Okay. Now we can find A. So angle A is going to be 180 minus the answer minus 19, 135.27. Now what? Redo the law of sines. Danny's got this down. Sine of 135.27 over little a is equal to, we have our choice, so we might as well use the b's. Sine of 19 over 6. So what am I going to type in? 6 sine of 135.27 divided by sine of 19. So, boy, that's 13 miles, right? So little a is 13 miles. Everybody agree? We should be saying no. We didn't do anything wrong, except maybe overlooking something. What did they tell us originally? Angle, side, side. Right? So, I knew angle B, this side, and that side, which is angle, side, side. Now, looking at that angle, side, side triangle, could it have two? Yes, because the second side is shorter than the first side. So if I were to create a circle around this 6, is it going to hit a second time? It has to, because it hit once and the second side is shorter than the first. Now, if this angle would have been 90 degrees, then there would have only been one answer. But that didn't happen. So we need to figure out this second angle. So if I'm going to draw this again. If I swing this over and it hits here, then I create this triangle. Well, this angle is 25.7, so this angle is also 25.7. So the alternate version for angle C is the supplement of 25.7. So 180 minus 25.7 is 154.3. How does that help? Now we have to create a new angle A. Right? Our goal is to find side little a. So we're going to add 19 to this and then subtract it from 180. So 6.7 is the alternate A. Well, luckily, when I recalculate little a, all I have to do is change this to 6.7. So if you go up, should be able to find that equation again. Shouldn't be too far away. And then instead of typing everything in, we're just going to change this to 6.7 and delete the rest. Oh, that did seem a little large. 6.7. So the boat could also be 2.15 miles away. So if you notice, as this looks out, as the lighthouse looks out, all it can tell is where the boat is. It can't tell how far it is, unless you had one heck of a rangefinder. But you have to be careful on these. Is it angle, side, side? If it's angle, angle, side, you're going to use sines. Do you have to worry about duplicate triangles? No. Angle, side, angle. Of sines. Okay? Side, side, side. Cosines. Side, angle, side. cosines. Angle side side, you have to, well, I prefer using the law of sines. It works with both, but we don't like the other version. So, okay, so let me draw that again, because that's a really good question. Anytime you have angle side side, angle side side, the second side is going to rotate around this joint, the one that joins the two sides. Okay? So as that rotates, it's going to create another triangle. Well, because this side and this side are the same, that means that this angle and this angle are the same. So whatever angle you calculated the first time will be the supplement of the alternate angle. And then you have to use that to find the third angle in order to find the side. Okay? All right, I just want to do one more with you, number 4. Two observers are 450 feet apart on opposite sides of a flagpole. So, here's one of us. Here's another one of us. 450 feet. And somewhere in there is a flagpole. Let's see. Flagpoles need to have flags, right? That's the math flagpole. The angles of elevation from the observers to the top of the pole are 23 degrees. So as one person looks up, creates 23 degrees. And as the other person looks up, creates 25 degrees. Is that flagpole in the middle? Why not? The angles would have to be equal. Which side is it closer to? Well, let's look at this. So if it was equal, then that's what the triangle would look like. Now the left angle is smaller, so to reach that same height, this angle would have to be larger. Does that make sense? So it's a little bit closer to the right side, the way that I've drawn it. Okay, because somebody said this person has to look up higher in order to see it, so they must be closer to the pole. Okay, what do we do? We do have angle side angle, which means we're automatically going to choose law of sines, which is nice. You might look at this for a while and think, man, I don't know where to start, but angle side angle, we only have one choice. We have two angles. Well, that you could, well, if so you're saying you can find this angle. That's true. And in fact, you're going to need to, right? But does that help us figure out the height of the flagpole? Not yet. But we have to use that to figure it out. That's a good point. What is that blue angle? 132. Okay. So we know that. Now we have angle, angle, angle side. So, right. Does it matter which side we find? No. Ooh, but it's not half. Right? So we'll get to that point. Let's find, I don't know, we'll call this x. How would we calculate x? Sine of 132 over 450 equals sine of 25 over x. So that's 450 sine of 25 divided by sine of 132. So the x value is 255, what was it, 255.9? Okay. Now what? What side? Do I care what this side is? I could find it, but it's not going to help. Okay, wait. Abe solved the problem right there. Let's forget about this stuff. We now have a right triangle. In that right triangle, because this is an altitude, and if those people are good at all, the flagpole is perpendicular to the ground. That's true. There's actually a leaning wall problem later on that you'll get to. So this is 255.9. This is 23. And we want to know this. I could use the law of sines again. I could do sine of 23 over x is equal to the sine of 255 over 90. Sine of 90. Or sorry, other way around. Sine of 90 over 255.9. But right triangle trig is much easier. Pythagorean theorem would work if we knew this side, but we don't. So if this is theta, this is opposite, and this is hypotenuse, SOHCAHTOA says sine of 23 equals x over 255.9. Whoa, that's just the law of sines, just written in a different way. Check this out. Sine of 255.9 over the sine of 90 is equivalent to x over, oh, that's not, sorry, that's 23. Is equivalent to x over 255.9. That's just the law of sines, right? Because I could divide by x and put the x here, and I could times by the sine of 90 and put it there. But what is the sine of 90? 1. So whenever you did right triangle trig with sine, you were doing a special case of the law of sines. The case where one of the angles is a right angle. Just like the Pythagorean theorem is the law of cosines, with C being a right angle. Anyway, when you solve this, 255.9 times the sine of 23, you get 100 feet. Okay. I updated the answers, but printed the wrong version. So